Let's turn now to a circuit which solves the problems outlined in the video before last. A really useful circuit, and one of the most important and common circuits in all of analog electronics, the emitter-degenerated common emitter amplifier. I'm going to discuss the operation of this amplifier over a few videos, but in this first one, I'm just going to go through the simple design procedure which will allow you to calculate the components simply and efficiently and get a working circuit. The circuit is shown on the screen. The DC blocking capacitors have the same purpose as described in the previous videos 67 and 14, and I won't describe them further in this one. The capacitor across the emitter resistor, CE, is shown dotted here because there are a couple of different options for it, which we'll discuss in a while. We'll demonstrate the design procedure through an example. Let's say that we have a 10 volt power supply, and we'll also choose IC, the collector current, as we did in the previous design example, to be 1 milliamp. So here is the design procedure. Firstly, pick VC, the collector voltage, to be VCC minus VEE over 2, for good bias, as we described previously. This puts it halfway between the voltage supplies, and means that in our case it's 5 volts. As with our previous example, this means that RC is VC divided by IC, which is 5 divided by 1 milliamp, which is 5K. Again, this is similar to the procedure in the previous circuit. Now here's where we depart, because in this one we have an emitter resistor. So let's make the emitter voltage 10% of VCC minus VEE. This is a common rule of thumb. In this case, because it's a 10 volt supply, this makes VE 1 volt. RE is VC over IE, and IE of course is basically the same as IC, so this is 1 volt divided by 1 milliamp, which is 1 kiloohm. The voltage on the base is the voltage on the emitter plus 0.6 volts because of the base emitter diode. This makes VB 1.6 volts. Now let's apply another rule of thumb here. Make R2 10 times RE. So this is 10 times 1K, which is equal to 10K. R1 and R2 act as a potential divider to fix VB, the base voltage, at the value which we've described earlier, which was 1.6 volts. The formula for R1 is shown on the screen and is just derived from the potential divider formula, and this makes the value of R1 52.5 kiloohms. So the whole circuit looks as shown on the screen. Now, a couple of points about this circuit, which I'll explain in more detail in the next few videos. Firstly, note that we didn't use beta, the transistor current gain, in any of the calculations that we did above, so this design is basically independent of it. Secondly, the presence of RE, the emitter resistor, gets rid of the problem of thermal runaway. I'll explain why in the next video. The capacitor CE across the emitter resistor has a vital effect on the amplifier. If it's completely absent, then the voltage gain of the amplifier is RC divided by RE. In this case, that would be 5. And the input impedance is approximately beta times RE, and the output resistance is RC. However, if CE is present, the gain of the amplifier is a few hundred, and the input impedance is a couple of kiloohms. The output impedance is again RC. Again, I'll explain why this is in the next few videos. The capacitor across the emitter resistor, CE, is chosen in a similar way to the DC blocking capacitors. It can be calculated so that its reactance is much less than RE at the frequency that we're trying to amplify, but in practice, many engineers will simply pick a suitable value from experience, which is large enough. In the next video, we'll take a look at how this amplifier actually works.